Hello, everyone. Welcome to my YouTube channel. Welcome to another episode of the podcast series, which I'm doing from so many days. You all know I started this podcast series mainly to discuss about the topics of health, education, and lifestyle. And in this particular episode, we are going to discuss about quantum computing, where we'll be having our eminent guest, Dr. Nishikanta Mohanty, a leading expert in quantum machine learning, SaaS analytics, and telecom data science. Here, in this particular podcast, you all know that many talk about quantum theory. Dr. Mohanty has been applying it to solve real world business problems. You are all very much interested about how to apply the quantum computing to real world problems. That is what this podcast talks about. He has worked on various related areas like marketing optimization to fraud detection in telecom. In this episode, we will uncover how quantum machine learning QML is reshaping the businesses in making decisions, optimizing campaigns, and handling the data. And more importantly, where like classical AI stops and quantum begins is going to be our topic of discussion. Not wasting your valuable time, I request you all to follow this particular podcast series from beginning to ending, and do like, share, and drop your valuable comments so that we can refine the content. It is really an honor to have you here. Can you please introduce yourself?
Likewise, Dr. Rajesh, I'm very happy to get connected with you and share this session. I'm glad that you have asked about quantum machine learning and its usage in real world. Uh, Quantum computing has been a huge hype, but not many people talk about the quantum aspect of AI. So let me introduce myself. So I'm a IT senior IT professional with 2 decades of experience. I have spent most of my career, like around 16 years out of it, in telecom. And I have used like I started like a simple developer from way back in 2005, with data warehousing and mining days. And then in 2010, I got my first AI and machine learning assignment with MTN Nigeria, where I developed certain prediction models and one classification plus a bit of hand-holding for marketing analytics, reduce the churn, improve cross-sale, and other things. That is my first step into the world of AI and machine learning. Then after that, I have worked on various projects and in various organizations. Telecom particularly was my domain, but then I worked into multiple other things. I worked in education also. I worked in products also in cross industry. I also worked in fraud detection and especially in telecom fraud detection. That means device thefts, handling like large volume sales and getting patterns about the companies or SMEs who can buy in bulk, but they can default at a time, which make the companies at a loss. Now I'm working in a social sector the same way with the fraud detection, anomaly detection, delivering better services to the of government to the disabled and other people. So that's my area, and right now I have also ventured into decisioning for last 4 or 5 years. So this is my overall expertise. I have had a PhD in quantum machine learning, but my PhD is not an academic PhD, to be honest. My PhD was more focused on industry use cases and especially applying those quantum techniques into real world problems that have been faced in AI and other domains, in optimization domains as well. So which will give an industrial perspective to the problem first of all, and also discover some novel methods to solve a problem that you used to solve classically. That's my whole things in a gist. I have till now developed 4 to 5 algorithms, and three are already published. Two are already in publication. Recently, I'm working on a quantum time series forecasting. We have already finished most of the things, but I mean, the preprint will be out probably by next month. So I have two more, in fact, three more people with me who whom we work collaboratively. And to be honest, like most people say that it's their achievement, but I think it's a collaborative achievement. So I work with them collaboratively. I'm the main researcher, and let me honest to you, I do the coding. I don't talk. I do the coding. I do the design, and our my colleagues also contribute to the design thought process, testing, and also benchmarking that and how it fits into an overall industry perspective. So this is the new way that I have discovered, and along with my guide Dr. Ferry, who is actually a big name in quantum machine learning and quantum AI space, and Dr. Chris Ferry, he has over like number of publications. He writes books. Like I can't be that great, but I try to learn from him, and I do whatever I do. I get a review and first-hand impression of him, so that before we could publish of such an algorithm. So this is overall my journey, and you can ask with anything you want. I mean, that's there.
Thank you so much, Dr. Nishikanta. It was really good to know about you, and you bring a lot of experience. It will be very useful podcast for those who really want to work in this area. Now, starting our discussion, how do you decide whether to apply a classical machine learning algorithm or a quantum approach for optimization tasks?
Great. So let's approach the problem in a different way. What does a machine learning solve? Machine learning or statistical analysis, what did it solve? Because we got computers, we started having data. Now we started having data, so we started to understand what we can do with data. Initially started with simple reporting, some analysis and all. Then we said, okay, can we get some intricate nature of the data? Can it tell us something? Can it predict certain events probabilistically? So we start to explore the geometry of data, develop certain techniques on it, and then try to predict some probabilistic outcome. That is essentially the machine learning. But you know that since our cloud came out, the hardware became cheap, the big data came out, there is a explosion of data in multiple cases. We have so many devices now with our hands, and everyone is generating data with different types of data. Initially, data means like a tabular nature, Excel sheet, spreadsheet, maximum, what I say, a database table. Now the data nature of the data is changing. Nature is hierarchical. Some data are complex, some are unrelated. So the nature of data is changing, and also the way we understand data is also changing. That means we are looking at a different geometry of data's nature. Now, obviously, the techniques that we developed are 30 years old. The AI techniques that we developed 30 years old, and they are right now relevant to solve the problems of data. But now when we are developing, which is a new intricate nature and complex nature of data, we also need new techniques. We also need complicated nature, or basically sophisticated algorithms. And classical computing has limitations. Though it's a evolved system, it's working well, it's all fine, but it has some limitations. Now to look at those limitations, we started to explore graphs, we started to explore knowledge, we started to explore vectors, the matrix way of looking into the data. Now in this way, like our techniques do not fit very well out there, or probably slow. So we started looking computing in a different perspective. Initially computing was actually 0 and 1. Now, for example, 0 and 1 means like a switch is on or switch is off. Now let's say we got a pendulum. We oscillate it. One state we say call 0, another state we call 1. Two ends. But what if the pendulum is in motion? That state is called a superposition state. We don't know where it is, but we can probabilistically say, oh, pendulum is somewhere. Similarly, Heisenberg's uncertainty principle, we cannot know the position and momentum both together. So that's how quantum computing is useful to us. Quantum computing is basically essentially using quantum effects or quantum principles to achieve computing. And quantum machine learning uses such and such technique. All that it do. But it's all that I said looks good for a story. What does a quantum machine learning or quantum computing do in reality? Just like a classical computer, there is a quantum computer. What you need to do on a layman's perspective, you have to send some signal to it. It will give you an output. But it has to be operated in a certain way. Because it's a chip, we can only give certain gates or certain things to it. And the things that we can manipulate is called qubit. So we have a qubit, certain gates, and we form together a circuit. We execute that circuit in a quantum computer and we get a probabilistic output. That essentially is quantum computing, very bare bones quantum computing. Or it's a gate model of quantum computing, but there are other models available. But most popular is the gate model. So when we say quantum machine learning or quantum AI, is basically re-engineering or tuning the classical AI or quantum machine learning algorithms in forms of circuits and in forms of quantum principle to achieve similar or better output. That's essentially is quantum AI. And when do we see when we jump between quantum and classical AI? Now, for example, fraud detection. Any scenario, bank, telecom, insurance, social security, anywhere. How many are the fraudsters? Fraudsters are always very, 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 very few. Now, because of fraudsters are few, it's what happens when we run a classical algorithm. It always it categorizes everything as good because good is 99%, fraud is probably less than 1%. So it will say this is called selection bias, or it basically is called as problem of unbalanced classification. It happens in the in the real world, and to mitigate such techniques, we use something called oversampling. We have something called downsampling. Downsampling is basically you take a equal sample of fraud and equal sample of non-fraud, and then you try to train a model on it. But then it is become very slow. Then we go to oversampling. So you boost the fraud with fake data or sample data. That's second one. So in either of the cases, you do not capture the whole pattern, right? So what classical machine learning does then is create something called SMOT, quantum or classical SMOT, synthetic minority oversampling technique. Looks very fancy, but in reality, what it tells that, okay, there are 100 fraudsters. Let me create another 100 fraudsters from the fraudsters. So that now fraudsters is 200, or I can create 300, 400, so that I can have a sizable fraud population that the algorithm is not biased towards always good. That's what it does. But how does it do? What it creates is like it treats the data, entire data points, entire data as a single point. Single point. Okay. Now between two fraud points, okay, there is a distance which we call the geometric distance or Euclidean distance. Now, if we put, let's say if we put something in between, we assume that anything that lies in between that distance is a fraud. That's how we create synthetic data in classical scenario. But what happens if the distance is too high, too large? So we create fraud in the regions of the data where the fraud should not exist. How to mitigate this problem? This problem is always there. So what we did is like we said, let's not talk about distance. Let's not do anything with the distance. We consider that data point, consider it as a vector and rotate it by a small angle. Quantum will do the rotation. So quantum will create, now from one fraud data point, you can create 100 fraud data points. That is the power of quantum machine learning. Instead of classical machine learning, which relies on neighbors or similar data points, you create data points from initially from its data point itself. That's how. Then that is possible because quantum provided something called rotation. Quantum rotations, very basic operation of quantum rotation, x, y, z, that rotation. We can also do a custom rotation, certain angle and all. We can create that. That power was not realized in classical before, which quantum made us realize, and it created quantum's mode, which was published before by our team. So that is one way. Another case is that the main distinction is that when you see a problem complex in nature, try some other technique, maybe it will solve, and quantum might come to your rescue. There is actually no line between when to use classical, when to use quantum. That's probably answers the first question.
Yeah. Yes, yes. Thank you so much. You have given a real insight where you have explained the main pointer regarding this particular topic, Dr. Nishikanta. Now, can you walk us through a real world optimization problem where
Mhm.
quantum algorithms provided a measurable advantage over classical methods?
Great. So I cannot disclose the customer name, but I can give you the overview of the problem. So what we have, proposed this solution, and it has created. We have created a prototype, but it's actually getting implemented probably. So what it is like you have we all have disaster recovery issues, right? Like floods, fires, rains, and other things. So or even emergency hospitalization in a city. Let's see, the problem is like it's a big city, lot of traffic, okay, and there are few hospitals around it, okay, and when there is an emergency, you need to respond quickly and get the ambulance there to get it back. But how many ambulances can you keep? Not for every case, right? Not for every case, not for every situation. That's not possible. Then what can we do? We cannot let lives lose, but we can minimize the risk of somebody getting medical chance, or we can increase the chance of somebody getting medical help in the emergency. How do we do this? So there's a network of hospitals, and every hospital has a set of ambulances. So those ambulances, we can plan to schedule them and place them in correct places in the city, so that time to pick up somebody in the case of emergency is minimized. That's the first problem thing. Second thing is that which hospital has availability for that kind of scenario. That's the second one there. So these two create something called a constrained optimization problem. You have traffic, you have ambulance, you have capacity, you have scheduling, and you have a network of hospitals. This is a graph splitting problem. Now, what you do is basically very simple technique is that you cluster the entire geographic location into clusters, get the mean of the centroid of the cluster, and put a ambulance center in each of them, or wherever that is compatible to that, and then see like wherever we can do that, and then calculate the distance of the hospitals which can be available, make the routes available, so which can be done. This problem, and if the city becomes big, and if we consider something like 2 to 3 cities together, then what happens is that we have to consider lot of more factors altogether. Distance to travel, what is their criticality. In case of ambulances also, there are other things inside. Maybe there is facility, there is no facility inside it. So all that we can convert it into a graph problem. First of all, graph to build a network of it, okay. Those node and placements we can configure, then we can place ambulances there, and from ambulances to the hospital we can configure a proper routing algorithm. Second, easiest routing. Then we can also configure another two more things, which is basically inside the ambulance, all the equipment aging, medicine expiry, that we can also configure. Plus we can schedule people so that maximum people are available for those kind of emergency services. This is a big enough problem. It's for system. Quantum comes to help. Quantum approximate optimization, D-wave fast tunneling, these solutions are useful there. And this has been considered for that. Second problem is that placement of disaster recovery location. Similar kind of problem. For example, you have flood across the city and you want to pump the flowed water into drainage. So you have to place drainage trucks or the pumping trucks. So those pumping trucks can be placed in a similar manner in optimization problem. These two can be easily achieved by quantum optimization, particularly D-wave annealing.
Those are the two excellent problems, Dr. Nishikanta. What challenges do you face when translating business data into a format suitable for quantum algorithms, and how do you overcome them?
Okay, so that's a great question. Actually, a lot of people do not understand how actually to approach this quantum optimization or quantum machine learning kind of scenarios. So data, what we understand is basically tabular data. Everyone understands tabular data. Other data people have difficulty in understanding. At least I have difficulty in understanding. So what happens is that, but whenever you are sending data to a quantum circuit, it has to be normalized. Means all the data points will be sum of the all square of the data points should be 1. So what happens is that we normalize the data points and we initialize them with quantum encoding. We encode them with quantum encoding. We get the output and then get the probabilistic output for each of the things. Once we get normalize the data, we have difficulty in denormalizing. So what we do is we keep a normalization factor with the data itself, the source data itself, and when we get the output, we can multiply the denormalization factor and we can get probably close to the first initial data. That's how we normally overcome or basically translate the data into a classical data into a quantum data, and quantum data back to classical data, provided we are using a particular type of encoding is called amplitude. But if we do angle encoding or other kind of encoding, it's difficult to get quantum data back to classical data. So the intent here is, if you want to get back the data, you should use simple encoding techniques. If you do not wish to get back the data, you only need the output, then you probably go for advanced encoding methods.
How do you choose between relational quantum algorithms and other QML approaches?
Okay, so variational quantum algorithm and other QML approaches. So what does a variational quantum algorithm means? It means running a quantum circuit multiple times with multiple parameters and achieving a certain objective till our objective is not progressing further. That is variational quantum algorithm. And that means it's either one circuit which is run multiple times, or it's basically layer to one or two layers of the same circuit repeatedly, but are also run multiple times. This is a traditional approach of QAOA. This one is particularly used for optimization problems. Okay, now let's say you want to use this for a machine learning problem. So machine learning problems can come in various shapes, like classification problem, regression problem, primarily these two, and neural networks, which is also one of these things. So classification is we identify a class, regression is we predict a number, and that's how it looks into. So the first thing is that we should concentrate. So variational algorithms versus the machine learning algorithms in quantum. So what happens is that machine learning algorithms basically predict either a classification or a regression algorithm, and they basically either predict a class or a number. That's essentially it. While the variational algorithms are primarily intended for uh, optimization scenarios, we can still use them for machine learning purposes. For example, support vector machine. It's a classification algorithm. Fraud detection. Quantum support vector machines can do much better than classical support vector machines, and and they have known to shown advantages. Okay, but how does a class support vector machine is made in a quantum algorithm? So what we do is, like in a variational circuit, There are two parts of a variational circuit. One is basically a cost function, which is basically taking that the problem we want to solve. And the second one is basically a driver, which is basically changing the cost function slowly. And then there are qubits, which basically on which it is acting. And qubits are first in superposition, then the cost function, then the mixer function, and then it repeats and repeats and repeats till it achieves the objective. What we can do is like we can encode the data and put it before the cost function. And similarly, we can add a decoding circuit after the cost function. This works like a support vector machine. It's an elegant technique to solve the problem. Another thing is that whenever we want to do any machine learning algorithm approach in quantum, what we are essentially doing, we are basically estimating certain uh, value or measuring certain loss. So in quantum, the measurement is basically something called fidelity, quantum fidelity. So that quantum fidelity can be measured by certain things like called swap test. So swap test is basically is similar to something called cosine similarity. Cosine similarity is nothing. It's basically if me and you, both pictures are put together, how both of our pictures are similar. How much overlap between us. Okay. It's basically looking at an iPhone. When you see a Face ID, so it looks at your picture and instantly unlocks. So what it does is like it stores your Face ID as a vector and captures your image as a vector and creates a similarity between the two. If the similarity is 90% and less than that or some certain criteria, it says you are a match, so you are gone. So in quantum, there is something called swap test, which measures the overlap of two quantum states. So if we intelligently use this swap test to measure between two data points or three data points, then we can have either a complete overlap or a partial overlap. If it's a partial overlap, it's a loss. If it's a complete overlap, it's a match. So if we continue to measure this loss and then manipulate this loss with certain kind of techniques, we can design beautiful quantum algorithms. That's how we transition between the machine learning algorithms in a quantum and an optimization algorithm in a quantum.
So, hybrid quantum classical solutions in projects like fraud detection or churn modeling.
Mm-hmm. Yes, it is possible. Look, what happens in churn modeling or fraud detection is basically what you basically prepare the data and then you supply it to a classical algorithm. Preparation means like this trimming, labeling, all that data preparation techniques, and then you give it to a classical or a machine learning algorithm, which creates a probabilistic probability of certain things of an event. Okay, so that's the way we approach either churn or fraud detection. Both are same because it's the similarly classification algorithm. In these both cases, we have to enhance or we have to boost the population by because churn population is also less and fraud population is also less. So we have to boost the population. To boost the population, we can use something called quantum smart. Okay. Apart from that, once we boosted this population and it has gone, then we have a choice. We can either go for classical algorithms like random forest, XGBoost, logistic regression. And if we go for quantum, we can go for quantum classification, simple quantum classification, or we can go for quantum, what I say, support vector machine, and even sometimes quantum neural networks. So it's basically first data preparation, and then quantum will then become like once you prepare the data, quantum is one of the options of the algorithms that you can choose. You can choose classical algorithm, you can choose quantum algorithm, whatever performs best on the data. That will be your choice of algorithm to go for.
Can you please give an example where QML improved decision making or campaign performance in marketing automation?
Okay, so it's basically identifying the patterns. So marketing automation and marketing optimization is all about patterns in the customer patterns. So when you look at various customer segment by usage or something like that, you can see a complete weird pattern. First of all, there'll be people who are spending very less. There'll be people who will have a consistent spending, which is basically considered medium to high. And there are people who are elite customers who are on the top end of that. Like, for example, if I say a normal customer, $20-$30 recharge, probably max. Medium range customer, enterprise, office going guys taking an iPhone, Samsung with them, that their spending goes to $100-$120. And there are some people who are basically top end executives. They are from, I mean, like their expense per month goes around $200 to $250. And there are some between like 150 to 200 and all these people. But these people are actually very less. So when you tailor a certain service, or a plan or an offer, you cannot give a $20-$30 offer to, to a top end CEO. That's not possible. So what you can do is basically you have to tailor offers different from them. So, but to distinguish these people, we can do distinguish uh, by your classical techniques and all. But what happens is that when you put them in a single place, the average normally uh, masks the elite customer. Like, lots of people have low segment. Even if somebody is in the high segment, the average actually comes down then. If many people are in a medium segment, if there is few people in significant, then the average shifts up. But then sometimes average comes down as well, which is quite classical. So what we do is basically you need to boost the population of those outliers.
Yes.
So what you can do is like you can apply a technique called angular outlier boosting with Smooth, which can boost the population of the outliers or the top end customers. And then you can, when you do you consider them as a class, then the class is coming as a significant benefactor for certain plans, which you cannot get it by normal campaigning or authoring. That's how you can do that. So angular outlier is nothing. It's like if you put the data, like the entire data set, there is a center of the data set. We call it the centroid. Now from the centroid, we calculate the angle of each data point. People who are laying in higher angles, okay, they are probably the outliers. And if you boost their population a little bit, then they come significant in your high-end plans, and you can market them. Which a segment that was completely hidden, now you can get it back. That's how it can enhance campaigning and targeting and also decision making.
Yeah, that's it. So, which quantum computing frameworks like Qiskit you
Qiskit is
found?
the most popular one, and everyone loves Qiskit because it is the first one which was mainly available. Everyone loves that, and Gate model, the tutorials are available. They are also very vocal about marketing it, like doing summer schools and all. And it's a nice way of getting started with quantum computing.
Yeah.
Then there are few more popular ones like Penny Lane. Everyone loves Penny Lane, but my problem with Penny Lane is it's very slow. And but it has features which is quite useful if we can intelligently use it. Then there is D-Wave Ocean, which is my first choice for quantum optimization problems. There is Fujitsu NLR also, which is another thing to look at. Now there are emerging platforms that is coming like Classic and Rickety Forest. They are emerging platforms. Also, Microsoft also gives QHash, but nevertheless, Qiskit remains the choice of platform. And then comes the D-Wave for enterprise application and mostly optimization things. So D-Wave is the next, Qiskit is the first. That is the two. that rule right now the entire space.
Okay. How to scale quantum solutions for large data sets in telecom and given the current hardware limitations?
Okay, so as I told you about something called a swap test to measure the fidelity between them. Now, swap test is an elegant method which can basically reduce the load of creating large enough quantum circuits or memory consuming processes. So what we can do is basically we can do something called a compact swap test. Okay,
Mm.
and in the compact swap test, the amount of qubits is basically significantly lesser than that. Means like I can give you an example. For 32 qubits, you 32 feature data set, or you sing data, you need only 5 to 6 qubit. Okay, and if you need 64, you probably need one more qubit. You give 128, you need one more qubit. So imagine like with 10 to 12 qubits, you can cover up almost 400 to 500 features, which is quite efficient. And in that way, if you create short measurable circuits and apply them diligently, then it will take away the problem of memory and hardware limitation. You can entirely bypass. This is what I do in all my algorithms in the research, and also wherever I advise. I told them that if you are going for quantum machine learning, don't go gung ho by giving them a large set of data and say that okay, our IBM or DU quantum computer will solve this. Try to design processes which are short, memory efficient, and can be executed in rapid succession. So instead of giving a large thing to solve, you can give smaller things in sequence or in parallel, and that will solve it. It's most like GPU. For example, you have CPU. You have CPU like Xeon, Threadripper, and what I say, Ethereum processors. All that they are heavy load GPUs, heavy duty GPUs. So CPUs to be together. But what GPU does? GPU is much less powerful than the CPU, but GPU has uh, cores which can do smaller tasks. But there are many cores of GPU which can do lots of smaller tasks at a time. So GPU becomes a parallel accelerator. Similarly, if we follow that design principle, if we create short quantum circuits which can measure one fidelity at a time, or one outcome at a time, then we can create quantum algorithms and quantum processes that is sustainable today and current hardware. Not, we don't have to look at 10 years in future that can do the things.
Yes. So, for aspiring data scientists who want to come into this particular field, especially in QML field, what practical projects or scenarios, use cases will help them to grow in their career, and what kind
Okay,
of hands-on
so
experience they
few
should
things
get?
they have to understand. They already are doing the classical AI, so they are aware of this kind of small scenarios, classification, regression, time series, what I say, neural network, all that they have done. So now let's look where we apply quantum here. Either we re-engineer the entire process in quantum, or we tune the output of the classical in quantum so that gives a better output. So these two ways are there. So if you want to re-engineer an entire process in quantum, they need to understand the mechanisms of the algorithm. For example, logistic regression or a simple linear regression. It what's happened? Ax plus by plus something and all. So we can say y equal to x1 beta 1 x2 beta 2. That is what the linear regression is. Now the key is here is estimating the beta, right? Now if you want to do it in quantum, people will say, oh, we'll put some circuit and mechanisms and all. No need. What we can do is we estimate those betas by classical, okay, and then tune those betas for the entire data set, which becomes a better quantum enhanced algorithm. That's one. Second case is that try to learn optimization. Now, optimization is a difficult. I mean, like machine learning is very popular. Optimization is not very popular, and you don't get courses like that. But you still get courses in optimization, which can give you tools like Pyamo, Gurobi, Cplex, using these optimizers. I mean, some Udemy, YouTube courses are there. You can do that and do some Python programming, and try to solve those optimization problem in quantum, which can be a discovery area for many as well. And it's not difficult to start. It's basically, it requires a bit of patience to go explore and re-engineer those process, and then giving it back and sharing the results.
Dr. Nishikanta Mohanty, you
Thank you.
have given really wonderful insights, practical insights, and use cases, which is very much needed for a quantum learner. It was really amazing to talk to you. In spite of your busy schedule, you have accepted my invitation and given valuable suggestions in this podcast. Thank you so much. It is very nice to meet you and learn all these things. And thank you so much, Dr. Nishikanta.
Thank you, Rajesh. I mean, thank you for speaking to me. And I hope, like, I don't do like a lot of things, but I think I could. I mean, I'm a very simple person. I try to explain the things the best way I understand. It's a bit technical, it is, because it's a machine learning thing, so has to be a bit technical. But I try to give my insights in the most non-technical way that I understand. Hope we can meet in future sometime, and I mean, I hope it can help people who are starting with quantum ML and solving real world problems and aspire to solve real world problems.
Exactly.
Thank you.
Really explained in very simple form, Dr. Nishikanta. Thank you so much. Thank you.
Thank you. Thanks a lot. Bye.